Okay, just going to do this question on a closest approach. So we've got two particles, particle A and particle B. We're finding the distance of closest approach between these two particles. So I could sketch a graph of these two particles here, particle A moving in this direction, particle B in this direction. At first glance it looks like they might intersect, but although their paths will intersect, they won't necessarily cross at the same time, and we're looking for the closest approach. So the technique we're going to use is the scalar product method, and effectively what we require is for the displacement of particle A relative to B, scalar product with the velocity of A relative to B to be equal to 0. If we can solve that for t, we can find that time of closest approach, and then from there work out the distance of closest approach. So first thing we can do is easily work out velocity of A with respect to B. So that's just the velocity of A, take the velocity of B. So just a straight up subtraction of these two vectors to get 18I take 12J. We'll also need the displacement of A with respect to B. So to do that, again, what we'll first need to do is define both the position vector of A and the position vector of B with respect to time. So you can see here, position vector of A with respect to time will be 30 plus 10t, bringing into account the velocity of particle A. And then we've got 10 take 5t. Similarly for particle B, position vector of B with respect to time it will be 54 take 8t, and negative 19 plus 7t here. So now that we've got both position vector of A and position vector of B with respect to t, we can then work out our position vector of A relative to B. So doing that, we have position vector of A relative to B will just be position vector of A take position vector of B. So it'll be this vector here, take away this vector. And performing that calculation, let me just move it up a little bit. So performing that calculation, we get negative 24 plus 18t and 29 take 12t. So at this point here, we're now ready to use our rule for closest approach, which is position vector of A relative to B, scalar product with velocity of A relative to B being equal to 0. In other words, the relative position vector of A relative to B needs to be at right angles to that velocity vector of A relative to B. That's why this rule works. Okay, so at that point there, we can now go and do that. So we've got our position vector of A relative to B here. There's our velocity vector of A relative to B. We just take the scalar product and set that equal to 0. Now that's easily done on your class pad. So doing that on the class pad, let me just move it over fraction. We'll just pull up a vector here, put in our values. So it's negative 24 plus 18. I'll actually use t as my variable. You could use x as well. 29 take 12t. And of course here I'll need to do the scalar product. So I'm just going to pull up my vector functions dot product. So you put in your first vector, so that's our relative displacement, displacement of A relative to B, and then we use a comma and put in our relative velocity, velocity of A relative to B, which was 18, 12, 18, negative 12 in fact. Close brackets equal, so it gives us an expression in terms of t here for the dot product of these two vectors here, and we actually want to find the dot product, the value of t when that scalar product or dot product is equal to 0. So from there we can do a solve. So I'll just go back to, just move that across a little bit. Go back to Math 1, solve, drag that whole thing in there, and set that equal to 0, comma, now I'm going to solve for t here. Just back to Math 2 to bring up t, and then execute. And you can see there we get t is equal to 5 over 3. So now, of course, here as well, these are a couple of steps where I found the scalar product of the two vectors and then solved, setting that equal to 0. Now that could all be done in one step. You could just put a solve in front of the dot product here, equals to 0, and that'll do it just as well. So this t is equal to 5 over 3 here. It's just the time at which we get the closest approach. Or if you like, the time at which the relative displacement of A relative to B is at right angles to the velocity vector of A relative to B. Now in the question we did want to find the distance of closest approach. So doing that again, what we need then is just moving back up here to our relative displacement here of A relative to B, which is this expression here. We want the value of this expression when t is equal to 5 over 3 because that's the time when closest approach occurs, and we want the magnitude of that particular vector because we're after the distance of closest approach. So at this point here we can then just find that magnitude, this magnitude of A relative to B when t is equal to 5/3, and again using the class pad this can be easily done. So at this point here I'm going to use my vector functions again, so vector, and this time I'm going to go to norm, which will find the magnitude of a vector. I want to put in that displacement of A relative to B, which is this one here, that vector there. So I'm just going to click and drag that down in there, and I want to find the norm value of that, and I want to find that when t is equal to 5/3. So I'm just going to use the this little function here. So it's basically this notation here is the magnitude of our displacement of A relative to B, and we want that when t is equal to 5/3. So I just, see if I can grab that t is equal to 5/3, put that down there, and hopefully that gives me the answer. There it is there, 3√13. So there's our distance of closest approach, 3√13.